Okay, let's get started with what I'll call optimization part one, dealing with the use of calculus to either maximize or minimize some functions. Part one will focus on application settings, a bit more accessible and familiar. Part two will be more abstract, dealing with situations that are a bit more unfamiliar. So look out for that. Paper one type approach using calculus, and paper two will be considered along the way as well. So here's a classic example to get started. We're a big carton being used for transport. It has to be constructed so that the volume is given 800 cubic centimeters, and the square base, which I've noted for you as x by x, um, allows for this height that I've called y, and we'll note that it is referenced that it's open-ended at the one end. So first task is to show that the surface area of this carton, S of x, which means the surface area is a function of x, can be written as you see here, and then we'll use that presumably to find the dimensions that will minimize the surface area. So look out for key terms like minimize and maximize when it comes to actually triggering calculus as the general approach you want to use method-wise going in. So what do we have? What we know is that the volume would be x times y because of the three-dimensional nature of a sort of a cuboidal type structure, which says that x squared times y is equal to the 800 that's given. So you've got some kind of relationship that's worth writing down. The surface area you're going to have to take, which is classic for IB, one surface at a time. So you've got, of course, the x times the y, which would be one of these surfaces here. And you've got four of those, and then you've got the bottom surface of x times x. So this idea of actually constructing the surface area, which you'll note here, S is dependent upon, or it's a function of, two separate variables, and that's going to be an issue for us to have to resolve. And since it is a function of two variables, there usually is a way to establish some kind of bridge or link between the two variables in question. And of course your link is right here. Your x squared times y equaling 800 allows you to solve for either x in terms of y or y in terms of x. Much easier to deal with y in terms of x, or namely y being a function of x, which allows you to replace the y value here with what we need. And a little bit of algebra, and you can see accounts for the fact that the first thing you were asked to do, namely to show that the surface area can be written in this form, you see that here. This guy is a classic reminder about this kind of 1 over b to the n equaling b to the negative n. That comes from your grade 10 variety of forms unit, so that's why we can claim what we have there. And so if we take a non-GDC paper 1 approach to actually try to do some kind of maximizing or minimizing, we need to actually minimize that surface area, I believe. So S sub x, which we now know can be written in that form, gives S prime of x, the derivative, pretty straightforward, as you can see here, in terms of applying the so-called power rule twice. And of course, by setting that first derivative equal to 0 and solving, you can actually flesh out the x value or values that minimizes or maximizes whatever that curve might look like. We'll take a look at it in just a second. Probably easiest to bring this guy back down, multiply both sides by x squared, and that accounts for this easier to work with equation here. Equate that to 0. That implies, if you divide by 2, that x cubed equals 1600, so therefore x is going to be the cube root of that, which would be an exact value form, which on your GDC would be approximately 11.7 if you took it out to 3 significant figures. And if you store that value as you should, if you're in a paper 2 context, and then consider the y value that goes with it, so you're most accurate in terms of the 3 sig fig rounding here. So these are the actual dimensions in question. And if you actually say, since you have the surface area as a function of x, if you plug that value in, again, I would use the stored accurate GDC value, not the actual 11.7. That would give you something that's roughly around 410. So Some of this, this is largely paper 1, a little bit of paper 2, because we're playing around with the calculator to give you an extension of the concept. Here is the graph. As it turns out, here is your surface area function. By the GDC notation, it's y sub 1. So a reminder that the surface area S that we're looking for is this function here, is this function here. And you'll want to note that the x value that comes in at around 11.7 that we found gives a so-called y value here of 410. My question to you is, when is y actually y? Well, there's kind of three things in play here. There's the x and y values representing the dimensions of the original structure, and then there's the GDC saying that this y value is actually the surface area. So be mindful of that, that y is not always y in the sense of you having to bring some reasoning to the setting. Okay, here's one where we'll go the other way around. We'll try to maximize the volume. So I've got a classic can in the shape of a cylinder, and it's got a given surface area. You can see two-dimensional, so it's an area. The radius of the cylinder having a maximum volume, so we can somehow maximize the volume of this guy, can be written in that form, classic IB, where you have to flesh out what A, B, and C are in terms of writing down ultimately those values after you find the R value that actually maximizes the volume. So what's classic here is if you think about a roll of paper towels and sort of cut that and open it up, you would get this piece here, and then you've got a top and a bottom because it's an actual closed cylinder shape. So classically, you've got to look at surface area from the point of view of so-called nets, right? And if you cut that guy and open him up, what you see there that goes around, that is the circumference of a circle, but that is going to be stretched across here now. And I'll call this H because it's consistent with H, and you get the idea. So if we go here and actually use what is a nets approach, right? I guess firstly, before we even have considered the net approach, we could have simply written down the volume of a cylinder, which is in your formula booklet. That'll sort of get things started. And if you look at each of these pieces, of course, the surface area would be 2 of these, hence twice or 2 pi r squared. That's what's coming in terms of these guys being added up. And then, of course, the circumference here, which is actually 2 pi rh, times h accounts for the area of the side surface, if you will. So that's what's established here. So here is our surface area equaling this rather challenging looking structure or function, if you will, equaling the 64 pi that was given, all right? So let's move on and say, okay, we have kind of an emerging bridge once again. If you sort of divide out the 2 pi, and you've got this more simplified structure, again, you've got this link between the two variables in question. In this setting, it's r and h as your two variables. And so we're trying to maximize this volume function, if you will. But here volume is a function of two variables, and that's a problem for us. So we need to express this as a function of only one variable. So by cleverly sort of saying, okay, we can talk about solving for h here in terms of r, so just bring the r squared over, divide both sides by r, you've got this form here. Maybe you want to use the common denominator idea here to actually work with this form. You have to decide which one of these two forms you think is easiest. So now the volume, which looks like this, can be thought of purely as a function of r, or that is dependent only on r, and that if you multiply carefully by distributive property, this term times this one minus this term times this one, you'll get this structure here. So that looks pretty good at this point. So what is this? This, of course, is our volume now, dependent upon or a function of just r, one variable. IB might write it like that, which can look a little bit more abstract and confusing to you. Or they could say let the volume be a function of r. So these are just notational forms that you might have to be reading. You don't always necessarily have to be using them, but you want to try to communicate as best you can. So what are we going to do? We're going to actually, as usual, differentiate this guy because we're interested in the role of the derivative as it's set equal to 0 to find the so-called stationary values. And the future of this graph, and I did throw it into the GDC later, it does actually maximize at some point. So the derivative, just to be clear, this is kind of a kx, leaving you with just k. And then this guy swings down, so 3 pi r squared. So again, these are just constants. And sometimes that's a little bit abstract and confusing to students. So let's set that derivative, as usual, equal to 0. And the only variable in question, of course, is r. Bring this negative term over to the right-hand side, so it looks like this. Divide, as it turns out, by 3 pi, and we get something that looks like this. Take the square root of both sides. Notice the plus minus concept here, which you always should consider. But of course, radius in this context will only be positive, so eventually we'll just be dropping the negative. All I've done is a little bit of sort of, again, grade 10 variety of forms units, sort of messing with this form here. And of course, the future of 32 is 16 times 2. The square root of 16 comes out as 4. So we get something that looks like this. Further, since we have not quite met the form that IB asked you for, it's close, we'll actually rationalize top and bottom. And so this form here now actually matches the form that they requested. And hence you can write down A, B, and C respectively as requested. Like I said, I threw this into the GDC for what it's worth. This function here is right here, and you see it does maximize at a particular point. So